Okay, so in this video we're going to talk more about forces, and specifically we're starting with the force of friction. We have named before some forces in everyday life, and we have learned how to draw a free body diagram of a given object. We have also studied how to find the x and y components of a force and how to find the net force acting on an object. In today's video, we're going to discuss more about the friction force, the types of friction that can be exerted by surfaces, and with how to find these magnitudes of these forces of friction, and how they vary with different applied forces on an object. So I will start my study of friction by studying this situation where I have this crater on a surface. With no applied force on this crater, the only forces acting on it will be a downward weight force and an upward normal force. And if there is no external or applied force acting on the crater, if this person is not pushing the crater, then there is no friction force either. So we end up with having the sum of forces to be equal to 0 and the object is still at rest. Now, if we start applying forces on this crater, so if we start making an applied force, a pushing force to the right, so right now I'm applying a force of 25 or 33 newtons to the right. You will immediately notice that we have an opposing friction force which is equal in magnitude to the applied force. So this is our friction, and it's increasing as we increase the applied force. The more applied force we have, the friction force increases accordingly so that they cancel each other. This is called the static friction. It is the kind of friction exerted when an object remains at rest. It's still not in motion. We will notice that we will keep increasing the applied force while the friction will keep increasing. But at a certain instant, with a certain magnitude of an applied force, the friction will no longer be able to cancel out this applied force, and applied force will overcome this friction and cause the crater to move. So this is the situation here. Once the applied force has reached around 130 newtons, the friction can no longer overcome this value, and the net force is now non-zero and the object starts moving. Now let's see exactly what happened at this instant. So we said this is around 130 newtons, so I'm going to move slowly. With a magnitude of 106, we're still with the same thing. 120, friction is still equal to the applied force. So around 120, we will start the motion. But an important thing for you to notice is that the friction, which was 100 something, once the motion starts, it will drop immediately into 94, as you can see here. In this situation, once the object is set in motion, the friction force changes and it becomes a kinetic friction. The kinetic friction has a different formula from the static friction. It's the friction exerted by surfaces when the objects are moving, and it is always smaller than the static friction. So you will notice that when we had static friction, it was always equal to the applied force. But once the applied force overcomes the friction, then we have a kinetic friction which is less in magnitude than the static friction which was exerted when the object was still at rest. Now that we have seen the experiment and the variation of the frictional force as we increase an applied force acting on the object, we can now draw some free body diagrams in order to analyze how the dynamics were changing as we increased our applied force and what was going on. So in our first situation, the crater had no external force acting on it, and this means that the only forces acting on it are the weight and the normal. And since there is no pushing force, then this means there is no tendency for motion for the crater. There is no attempt at sliding, and you can deduce that there is no friction either. So the only forces we will have are the weight, which is downwards, and the normal, which is upwards. And this object obviously will remain at rest. It's in equilibrium. Next, we started with applying an external force on our crater. So let's assume we're applying a force of magnitude 92 newtons to the left. And then you can see immediately a friction force exerted in the opposite direction. So if we draw the free body diagram, we'll have weight, normal, friction and the applied force, we can notice that the applied force is always balanced by the frictional force. So we can see here we have written friction is equal to the applied force, and then the crater remains at rest. And even as we increase the applied force, so you can see here we increase the applied force to a magnitude of 125 newtons, the friction increases as well to balance this force again. So we still have more applied force, more opposing frictional force, and the object is still at rest, there is no motion. But finally, at some point, the applied force will overcome this friction. And you can see here, once we reach 126 newtons, there is a net force exerted on the object, and there is now a non-zero speed for the crater. It's moving in the direction of the applied force. But let's also notice something else. The friction force is still there, but its magnitude has actually decreased. So you can see here when the applied force was 125 newtons, the friction was also 125, but once we increased the applied force to 126 and the box started moving, the friction drops to a value of 94 newtons. So this is because we have a new kind of friction once the object is in motion. When the object is in motion, the friction exerted on it by the surface below this object is going to be a kinetic friction, versus a static friction that is exerted by the same surface on stationary objects. So if the object is not moving, the friction is called static friction, and it has a value more than the situation where the object is moving, where we have a kinetic friction. So the kinetic friction is always less than static friction, and that's why the value of the friction drops from 125 to 94 once the object is set in motion. We can see here a free body diagram showing the situation where the crater is set in motion. So this is the applied force. The friction is opposing it. And now we have a non-zero acceleration. But the friction now is called kinetic friction. It's not static friction. Now the box is moving and accelerating in the direction of the net force. One thing we can do is that we can reduce this applied force again so that it's exactly equal to the kinetic friction. And then the net force will be zero again, and the crater will keep moving but in a constant speed now. So this is the situation here. We decrease the applied force to be equal to the kinetic friction, which is 94 newtons, and then the sum of forces is now zero. The forces balance each other. The crater remains in motion by Newton's first law, but now the motion is in a constant speed. We can see this graph here, which shows us the variation of the friction as we increase the applied force. So at first we had no applied force, so there was no friction because there is nothing to oppose the motion. There was no tendency of motion in the object from the first place. Then as the applied force increased, the friction force emerges and increases as well. We are still in static friction. The static friction keeps increasing as we apply more force to push the crater until it reaches its maximum value. After this maximum, if we increase the applied force, the object will start moving, and once the object starts moving, the friction drops to a kinetic friction value, which is constant even if we increase the applied force. So note that the kinetic friction is constant, while the static friction increases as we increase the applied force. So we have two types of friction, the static friction and the kinetic friction. The static friction increases as we increase the applied force, while the kinetic friction is constant. The formulas for these frictions are given here. So the kinetic friction is equal to mu k times n, where mu k is the coefficient of kinetic friction. It's a constant depending on the surface on which this object is moving. A rougher surface will have a higher value of coefficient of kinetic friction. Multiplied by the normal, this is the magnitude of the normal force. The static friction increases as we increase the applied force, so it's always equal to the applied force that is trying to move the object. But at the maximum value, the static friction will have a value of mu s times n, where mu s is the coefficient of static friction, and n is the magnitude of the normal again. It's important to note that both mu k and mu s, which are constants, both of them are both always less than 1. Of course, the higher their value, the rougher the surface. An ideal frictionless surface would have mu to be equal to 0. So basically, whenever we're asked about the friction, we can use these formulas. The static friction has a formula for the maximum value only. Otherwise, it's equal to the applied force itself. And we can always remember to use Newton's laws to find the value of the static friction in this case.